In 1929, Edwin Hubble looked at distant galaxies and noticed something that changed everything. They were running away from us. Not some of them, all of them. And the farther away they were, the faster they were fleeing. The universe wasn't static. It wasn't eternal and unchanging like scientists had assumed for centuries. It was expanding, violently, in every direction, all at once. From that observation, you could run the clock backward. If everything is moving apart now, then everything was once closer together, close enough to touch, close enough to compress into something unimaginably small and hot. The math gave you a beginning, a birth, a number. That number is called the Hubble constant. It measures how fast the universe is expanding. Get that number right, and you get the age of the universe right. You get the size of the observable universe right. You get the entire timeline of cosmic history right. For decades, we fought over that number. Early estimates disagreed by a factor of 2. Careers were built and destroyed arguing over it. Then, in the 1990s and 2000s, we built better instruments. We launched the Hubble Space Telescope. We measured with unprecedented precision. The community converged. The numbers settled. We declared the problem solved. We were wrong. Here's what's happening right now in real time inside the physics community, and what the viral headlines got almost completely backwards. There are 2 primary ways to measure the Hubble constant. 2 independent methods built on entirely different physics, pointing at the same number from opposite directions. The first method looks at the early universe. It reads the cosmic microwave background, the oldest light in existence, the faint afterglow of the Big Bang itself, imprinted on the sky 380,000 years after the universe began. The Planck satellite measured this with extraordinary precision. It gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second method looks at the late universe. It uses a cosmic distance ladder, Cepheid variable stars whose brightness pulses in a predictable rhythm, Type 1a supernovae that explode at a known luminosity, standard candles that let astronomers calculate distances across billions of light years. The most precise version of this measurement, led by Nobel laureate Adam Rees, gives a Hubble constant of approximately 73 kilometers per second per megaparsec. 67 versus 73. That sounds like a small difference. It is not. These measurements are now precise enough that the gap between them cannot be explained by instrument error. It cannot be explained by calibration mistakes. Both teams have checked their work repeatedly, obsessively, for over a decade. Independent groups using entirely different tools, gravitational lensing of distant quasars, surface brightness fluctuations in galaxies, the sound waves frozen into the large-scale structure of the universe, keep landing on one side or the other. The universe is simultaneously 2 different sizes depending on how you measure it. That is not a rounding error. That is a crack running through the foundation of modern cosmology. The viral articles called it, "Physics is broken." That framing, while dramatic, accidentally understates the actual problem. Because the real issue isn't that physics broke. The real issue is that physics is giving us 2 internally consistent, independently verified, mutually incompatible answers about the most basic measurable property of the universe. And neither answer is wrong. Think about what that means. The Hubble constant isn't an obscure parameter buried in a specialist equation. It is the number from which we derive the age of the universe. At 67.4, the universe is approximately 13.8 billion years old. At 73, it's closer to 12.5 billion years old. That's a difference of more than 1 billion years. 1 billion years of cosmic evolution. 1 billion years of galaxy formation, star birth, planet chemistry, and potentially life. Either present or absent, depending on which measurement you trust. We don't know how old the universe is. Not to that precision. And we've been stating that number with a confidence we have not earned. But here is where the story gets genuinely strange. Because the Hubble tension isn't just a measurement problem. It may be pointing at something real. A structural feature of the universe itself that our standard model, for all its success, simply doesn't contain. The standard model of cosmology is called lambda CDM. Lambda for the cosmological constant, dark energy. CDM for cold dark matter. Together they describe a universe made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It is the most successful cosmological model in history. It predicted the distribution of galaxies we observe. It predicted the acoustic peaks in the microwave background. It explained the accelerating expansion. And it cannot explain why its two best measurement techniques disagree about the expansion rate. Some physicists have proposed that dark energy isn't constant, that it evolves over time, stronger in the early universe, weaker now, or the reverse. This would change the expansion history and could pull the two measurements into agreement. But it would also destroy the cosmological constant, one of the foundational pillars of the Standard Model. Einstein's greatest blunder, which turned out not to be a blunder, would become a blunder after all, 50 years later, in the opposite direction. Others have proposed early dark energy, a brief burst of additional dark energy in the first fraction of the universe's history that accelerated early expansion just enough to reconcile the numbers. It's elegant, it's mathematically workable, and it creates new problems with the large-scale structure of the universe that don't have clean solutions yet. There is a third possibility that almost nobody says loudly, but that sits underneath all the others like a fault line. New physics. Not an adjustment to existing parameters, not a revised calibration. Something fundamentally absent from our current framework. An ingredient we haven't discovered yet, that operates on cosmological scales, that leaves one fingerprint in the early universe and a different fingerprint in the late universe, producing two genuinely different expansion rates depending on when you look. What that ingredient is, nobody knows. It has no name yet. It may not even be a particle or a field in any sense we currently recognize. It may require a revision to general relativity itself, to the theory of gravity, the scaffolding that holds all of modern cosmology together, at scales larger than we've been able to test. That is the actual scientific situation, not broken physics. Physics encountering something it was never designed to describe. Now here is what the public conversation missed entirely. The James Webb Space Telescope, the instrument that was supposed to resolve this, has made it worse. Webb's measurements of Cepheid variable stars, the first rung of the distance ladder, confirmed Rees's higher value. Webb didn't find a calibration error. It validated the discrepancy with greater precision than ever before. The gap didn't close, it sharpened. At the same time, new analyses of the cosmic microwave background continue to confirm Planck's lower value. 2 instruments, 2 methods, both more precise than anything we've ever built, both disagreeing more confidently than ever. The precision of our tools has not solved the problem. The precision of our tools has proven the problem is real. And this is the thing that the viral headlines, the explainer videos, the breathless science journalism all quietly walked past. The Hubble tension isn't a temporary embarrassment that smarter scientists will patch up next year. It has survived every attempt to explain it away for over a decade. It has survived new telescopes, new methods, new independent teams approaching from entirely different angles. It has not weakened. It has hardened. The universe has been patiently, consistently pointing at something we don't understand yet. Not at the edge of observability, not at some exotic extreme of density or temperature, not inside a black hole or at the moment of the Big Bang where we expect our models to fail. Right here, in the current universe, in the expansion we can measure directly, in a number first written down in 1929 that we thought we understood a century later and don't. Edwin Hubble looked at the sky and found that everything was moving away. He had no idea what he'd actually started. We measured the rate of that flight with the finest instruments in human history, and the universe gave us 2 different answers. Both correct, both real, both impossible. We're still standing in that room, staring at the numbers, waiting for the universe to explain itself. It hasn't. And that's it from this video. See you in the next one.